Das. I'm an assistant professor in the Department of CS, IIT Jodhpur. So I'll be chairing this session, and we have next round of speakers, and I'm very happy that you guys are asking so many questions. I hope that you will continue to do that. And thank you, Dr. Sumit, for this opportunity. So we will welcome our next speaker, Dr. Urvi Chatterjee. So she is an assistant professor in the Department of Computer Science, IIT Kanpur. She did his masters from ISM Dhanbad in 2013. After that, he did his PhD from IIT Kharagpur at 2020. She is working in hardware security and computer architecture, side channel attacks, network architecture. So we welcome Dr. Urvi on stage. Yeah.
Can you hear me? Am I audible? Okay, good. Okay, so welcome all of you in the post-lunch session on hardware security. Today we are going to talk about a few test cases in hardware security. What are the trends that are currently going on, and what are the future problems that we are trying to deal with before they become really critical. So that's why the title of the presentation is the present and future of hardware security for embedded systems. So in our lab, we do a lot of hardware related attack methodology development and countermeasure. Mainly we focus on side channel attacks. We designing hardware using Verilogs and VHDLs. We also work on timing attacks on network on chip, physically unclonable function, and so on. So I'm not going to go too much of details of this, just to show you the different varieties of attacks that are already present at the lowest level of a system, at the hardware level. So now just a brief introduction to my team. I joined IIT Kanpur in March 2021, and then Devopriyo joined 9 months after that. And this is our team right now. All of them are PhD students, and the team is not complete without our funders who are funding our research across different perspectives. So these are some development that we have done in our lab. So we have a side channel secure efficient hardware design for post-quantum cryptography. We work on acoustic side channel attacks, screen reading attack for OTP extraction from mobile phones. We have far-field side channel attacks, EM side channel attacks. A lot of authentication work is going on for swarm of drones. And also we are collaborating with few abroad universities for biochip security. So now let us give a brief introduction about hardware security and side channels. So suppose Alice and Bob wants to talk to each other securely, okay? So they will definitely use encryption. Now when we talk about encryption, the algorithm that comes into our mind are AES, DES, RSA, ACC. Many of you are aware of them. So now these algorithms can be implemented in two different ways, okay? Using software code, you can write them and implement them, and there is a way to create a co-processor to dedicatedly do that stuff, okay? So that is what we call here as hardware, okay? And we do Verilog programming to design that hardware that will only do that application. So if you write as AES code in C or Python, what will happen? we have to create that, we have to compile that code. It will be a assembly level code, then it will be converted into instruction, and that will go to a general purpose processor, which will only accept this program as the specified instruction in which he can talk to the upper level softwares, right? So now, to make this thing faster, we create a separate crow processor using Verilog programming. So, now whether we do a software implementation or hardware implementation, the attacker will try to sniff the channel which is encrypted and used for the message passing. So, the theoretical cryptographer, they try to make sure that okay, this algorithm should be protected against mathematical cryptanalysis. Okay? Now comes unfortunate people like us. We do hardware engineering. Okay? We take the algorithm and we try to make a hardware out of it using something called Verilog. Okay? So we define that algorithm with respect to registers, memory, and definitive instruction or finite state machine implementation of that particular application. Now, this is how our algorithm will look like in hardware in terms of gates and multiplexer and other logical implementation, and then we will implement them either in FPGA or in ASIC. FPGA means field programmable gate array, and ASIC is application specific integrated IC. Okay. So this is where your hardware implementation of AES or ECC runs. Now, what has happened since 1988 is, when we implement these algorithms in hardware, they are prone to different kind of hardware level attack, where the attackers does not try to break the algorithm. Okay? The amount of power you are drawing to run that hardware, or the EM signal that is getting emanated from your hardware, or the time it is taking to run the hardware, or a single fault while you are executing the algorithm in hardware actually can leak information about your secret key. This is called side channel attacks. Okay? Now these three are basically conventional side channel attacks that in present we are doing for a long time. Now comes acoustic side channel attacks. Okay? These acoustic side channel attacks can not only help you to break a cryptographic algorithm, but it can do much more. Okay? So in future, we are trying to see what else that these side channels in terms of acoustic can do to your hardware system. Clear? So first of all, let us see why acoustics or sound gets generated in our hardware. So if you see, the piezoelectric and electrostrictive effects of the metal used in capacitors results in the capacitor inter-electrode to vibrate, causing a chain reaction. So the vibration is transferred from the inter-electrode to the capacitor terminal, from terminal to solder joint, and finally to PCB, causing something called singing capacitor phenomena. Okay? So from electrode to the in the electrode they vibrate with respect to current, then they expand with the electric field, and then it comes to the solder joint, and then it comes to PCB. Okay? Now, if you just have a stethoscope, you can actually listen to these inaudible signals like our heartbeat. Okay? So if you have seen Harry Potter's and Order of the Phoenix, you remember a scene where the Order was doing a meeting in Sirius Black's family house, and Weasley brothers hang a ear to listen. So this is the ear which is helping us to listen to our PCB. Okay? So what we can do, we can build a disassembler. What is disassembler? We are running a set of instruction. This acoustic sound actually depends on what instruction currently I am running into my machine. So this acoustic side channel can help us to understand the code, or something malicious is happening within a known code directly or indirectly to detect any malware. Okay? So what we do is, so this is a very simple setup. You can do it in your institute or at your home as well, we take an Arduino board, okay? We take some clay and we fix the earbud of the stethoscope tightly on top of the Arduino board, okay? Now the later part or the back end of the stethoscope is connected to a Bluetooth speaker, and that Bluetooth speaker is wirelessly connected to my phone speaker. So whatever sound my processor is generating, that is getting recorded in my mobile phone. It's a proof of concept device design, okay? So now while I'm running an assembly code in my Arduino, depending on what instruction is running, the capacitor will vibrate, and that vibration will be recorded, and later on they can be analyzed. So what we started with is single instruction and no operation, okay? So what we have found that there is significant difference between the acoustic signature of these two. So we have understood that stethoscope is running, and it is actually helping us to distinguish between no operation and some operation. So we did that. After that, what we do is that we divided the instruction set of Arduino, which is having Atmega microcontroller inside it, into 4 different sets or 4 different groups. How? The instruction that takes 1 clock cycle to execute, the instruction that takes 2 clock cycles to execute, 3 and 4. And we have seen that just by simply capturing the acoustic signal and analyzing them in MATLAB, we can understand that whether it's a 1 clock cycle, 2 clock cycle, 3 or 4 clock cycle instructions or not. But we want something more than that. We want exactly what instruction is running right now. So then what we did, so this is the program that we ran, and we collect the acoustic signature like that, and then we took help from ML Baba. Okay, so what we do, we actually find out what are the very useful features of audio signal. In our case, it was spectral centroid and spread, spectral flux, and much important feature is male frequency spectra coefficient. Okay, you see any paper or any study about sound signal processing, this MFCC is one of the most useful feature that is there in any sound signal. So similar to these 3, we find out using MR algorithm what are the most useful feature in the sound, and then we actually first classify the sound signal to find out the group, and then we run machine learning algorithm to exactly find out that what are the instructions that is running on my Arduino board. Okay, so up to this part it is very easy, and you can actually replicate this instruction at your home. So today whatever we are going to discuss, you can actually replicate it. So not so important thing, our accuracy varies from 82% to 90% so far to find out what exactly the instruction that is running on the Arduino board. So it was the initial result, and then later on over the time we have actually modified or improved the results. So now given this, what we are planning to do in future is that it has just one microcontroller, right? So now we are trying to see that what is the impact of acoustic signals in multi-core processors, okay? And we have found out that actually in iPhone, it can detect which code is running what instructions, and then which application is currently running, okay? And if you change your location while you are talking to phone, the attacker can be on the phone call with the victim and find out your location is changing, okay? So these are some future privacy related research that you can do in future to exploit more on acoustic signal for privacy and security attacks on smart devices. So the takeaway is, can we do acoustic based instruction based disassembly for multi-core processor? Can we do application or activity identification in smartphone using acoustic? And can we build a metric about how much information a system is leaking through acoustics? So these are some work that we can think about in future. Now, yes.
So in a circuit, right, with processor, there will be lot of capacitors, lot of different circuits are there.
Yes,
okay?
yes.
And like still you are able to, so won't the signal be too noisy to figure out?
Yes, there will be noise. So what we do is that when we do no operation, the signal, still we get some signal. So we take it as a standard noise. And then whenever we do side channel attack, no, we have have to do noise cancellation process to actually extract the signal. Rather, I would say if you analyze these signals in frequency domain, that also helps, because the capacitors that are very close to the processor, the general purpose registers, they work in a particular frequency. So we filter out the rest of the frequency domain signals and just focus on that. So that's why we have to take a lot of traces and then we can do it.
And also, is the latency of the instructions provided that it's usually confidential information, or is it given out in the data sheet when you classify the instructions into, let's say, 1 cycle and 2 cycles? Is that
This information available in Atmega's data sheet. Yes, yes. Even in if you see ARM, in every data sheet,
Because usually, yeah, but they leave the microarchitecture, but they give you which.
when we tried to do it in Apple, it was quite difficult. It was quite
Yeah,
difficult.
because ARM license the ARM license will their own. So
Huh.
they'll
Yeah. But still the privacy leakage was pretty easy. So the attacker can actually do a first make a template on his own phone and do a phone call to you if he knows what model you are using, and then the person will just talk to you, and he can actually record those conversation in his phone and find out what are the application that is running on your mobile phone while you are talking, or whether you are moving from one place to the another. These parts we get lot of nice accuracy. Now, something totally different, okay? Because I said today I will give a little bit of glimpses of many things. Many of you must know about timing side channel attacks. So before going to that, let us see what is network on chip and why we are talking about it. Okay. So nowadays this MPSoCs, multiprocessor system on chip, they are coming with amalgamation of lot of small chip inside it. Okay. So in standard computer, I'm not talking about GPU and all for now. What we have seen, we have a processor, okay, we have cache, we have main memory, and they are talking to each other. The inputs are coming from different input output ports, and output are going to the output ports, right? Now, because of the high demand, we are making many high-end devices like these MPSoCs, and what we are trying to do in future is that creating a network interface between different IP cores. Right now it is just a bus. We have data bus, address bus and all. Now we are coming up with the thoughts of having a router which is connected to this processing element. This processing element can be a processor, it can be a memory, it can be a router, it can be anything. But it will be a network of such processing element, okay, for faster computation. Okay, so this kind of structures we are simulating. There is a company named Tylers. They have actually come up with a 4x1 such network on chip architecture. So now we all know that our standard computing system are vulnerable to timing attacks and cache attack, right? What is that? We are running an AES, and when we run software implementation of AES, we use something called T-table implementation. Okay, do not need to go into the depth. T-table is kind of a lookup table that we store in the cache, which is the closest to the processor, and depending on whether AES process is fetching the data from the T-table or not, the attacker can actually understand what is the secret key. So all this cryptographic implementation, they are data dependent, plain text dependent, and the secret key dependent. What the attackers look for is how the timing or EM or power are dependent on the secret key, and that's how they break everything, be it a software implementation, be it a hardware implementation. So now, given this small brief, I cannot cover timing attack a lot in this small time frame. What we have seen is that all these timing attacks are also possible in network on chip if one of my processing element is running AES into it. Okay, so since 2012 the baseline attack started coming, and in host 2021 a very strong attack named Knock came, which actually exploit cache hit and miss to understand whether AES is running on a particular P, and if it is running, what is the secret key. But in all those attacks there was a problem. What was the problem? They assume that when the AES is running in a P and it is accessing the cache or the level 2 cache for this T table access, they are going through some network path, okay, because we are talking about network in the network on chip or system on chip, and the attacker must lie within that critical path. Okay, so we did a small work to find out that how the attacker will know that whether he is sitting on the correct path or not, right? Because it is not one processing element, one memory and one main memory, right? It can have multiple processing element with multiple memory. Okay, so whether the attacker knows that what is the layout of the MPSoC, that can be done using this particular attack that we have proposed. So a brief that I gave you, timing attacks actually exploit the time that is used to run a AES or RSA algorithm and find out the secret key. Now in network on chip, the main crux that we exploit is tracking the throughput of a particular processing element. So we have multiple processing elements and every one of them are connected to a router. That's what we have said, right? Now suppose this processing element 0 wants to send some data to 3. Okay, if there is no other packet in that path, it will swiftly go, right? But suppose B is sending a data as well as, 0 is also sending a data as well as 1 also is sending a data, right? And they are going through the same path. So now two packets are passing through the multiple P element. That will create something called congestion in the path. So the attacker actually now try to track this congestion in the network chip to find out the secret key. How? Suppose in this P0 we are running RSA. Okay, RSA is an encryption algorithm. It's a public key crypto system, and then we have attacker sitting in PE1 and we have a shared cache in PE2. Now as we know, in RSA, if the secret key bit is a squaring operation, then secret key bit is 0, then a squaring operation will happen, whereas it is 1, then the squaring and multiplication will happen. Now, if for some reason the P0 wants to fetch some data for 0 or 1, it has to go to the shared cache, right? Now what the P will do, P1 will do, whenever it is generating some request, it will create contention. Okay, if it is a one squaring operation, then the contention will be low, but if it is a one bit, then the contention will be high because P0 will do two requests to the L2 cache. Okay, so depending on how much contention is getting generated in the path, the P1 will understand that whether the current secret key is 0 or current secret 1. I tried to make you understand as simply as I can. Things are complicated much more than this, but this is the main thought process behind doing timing side channel in network on chip. So when we do attack, we have some assumption that the attacker target the MPSOC that can have any kind of routing algorithm and any kind of topology. It can have maze topology or torus topology, but the attacker needs to know the topological order but not the routing. So knowing whether the P's are connected through maze topology or not, that's all the attacker needs to know. Okay, but the attacker does not know which P is connected to which P. Okay, so this is the target of the attacker, to reverse engineer the layout of the MPSOC. Next is the attacker can control one of the P and run a malicious program like remote access tool on the MPSOC to get allocated on that particular P. And then the malicious program gets allocated the P by a mapping algorithm and the attacker does not need to know that which P has got the program. Okay, it can be any one of them. So far in all timing attack, the attacker knew exactly where it is situated and it must be situated between the path between the the target and the shared cache. Now the attacker should have the ability to communicate with all the P's in the MPSOC either by requesting an appropriate shared cache block that maps to the LLC bank attached to P or by crafting a packet containing proper destination address of the required P. And finally, the attacker must be able to send concurrent ping requests to multiple P's. Okay, these are all very generic assumption depending on the specification of an MPSOC that implements network on chip. Now, I will give a very brief of the attack what the attacker is doing. So, this is the bad P, okay, and it has 3 more P's. So, P1 and P2 is directly connected to P and P3 is connected to bad P through this P2, okay. So, here no cryptography is required to understand this thing. Okay, we are not going to the cryptography, just understanding the reverse, just doing the reverse engineering of the NOC. Now what we are doing is that this P will start pinging first all the P's concurrently. Okay, so the P that are closer to malicious P will reply faster, right? And the P's which are farther from the malicious P will have some slow response. Okay, so the attacker can actually group depending on how long it is taking to get the request response. So this P1 and P2 will be in one group, whereas this P3 will be in the different group. Still understand, so this is a dummy architecture that we have taken. Okay, now the attacker does not know yet that whether this PE is connected to PE2 or this PE is connected to PE1 or not, right? It just knows the timing, right? Here all we are here in caching is the timing of getting a response. So now what it will do, it will create a contention here as well, one by one, and here. So when we are creating a contention here, because P3 is not connected to P1, the time to get reply will be same as previous one. Okay, but when I am creating a contention in P2, contention means flooding with dummy requests. Okay, then it will take some time because we are filling up the bandwidth. So the time to get reply from P3 will be more. Okay, as a result, the attacker will understand that P2 is actually connected to P3. So this is a very simple example. The more P will be there in a network architecture, a network on chip, it will be much more complicated, but we definitely can make up an algorithm and find out the whole layout of the particular MPSOC. Now, once I know where I stand, in future, for future, we are planning to show that this particular attack can be amalgamated with timing attacks in network on chip to break AES key without placing this particular adversarial P in the critical path. That is between the AES key which is running the P and the shared LLC. Okay. And also we are, for future we are trying to find out that there are certain countermeasures that has been proposed in the literature, but give all of them consider that the P is in the critical path. So none of them will work if the P does not need to be in the critical path. So we are framing countermeasure also to find out how to stop this kind of timing attack on network on chip. Not required. So how can reverse engineering attack can be integrated with traditional timing attack? How can we develop attack methodology where adversarial P does not need to be in the critical path, and how to develop countermeasure. These are the 3 takeaway for now for our future. Now we are going to something which is quite relevant in today's hardware design and all. So have you heard of hardware Trojan horses? Anybody? No. Okay, let me explain. Hardware Trojan horses are the hardware version of software malware. Okay, what it does, but the problem with hardware Trojan horse is that if you insert it into the circuit, it will remain in the circuit. You cannot delete it. Okay, and what it does is it actually try to be triggered in a very rare input combination of the circuit, and then when it is getting triggered, it try to extract information from the circuit. If you are having a hardware code running in a system, maybe it is running AES algorithm, it will try to fetch the secret key just by doing some tweaks in the circuit. Okay, so there is a lot of work on impact of such hardware Trojan in AES, in RSA, in SCC hardware implementation. Today we are going to talk about hardware Trojan horses in approximate computing hardware. Why it is so important? So approximate computing has been massively used for data processing application. Specifically for ML AI accelerators, when we talk about at the lowest level processor design, we do approximation. We do approximation in terms of computation, we do approximation in terms of data, in terms of data storage as well. So data storage as well. So approximation we can do at any level of the application. We specifically focus on lowest approximate adders and multipliers that are used for ML accelerators. Okay, so the testing problem with approximated adders. What is the problem? So suppose I have created a hardware for addition. So whenever I will give 5 plus 3, it will give me 8. The output is always constant for the given input. The problem with approximate adders and multiplier is that it sometimes can give me 7.5, it can sometimes give me 8.2. Okay, so but it should be in a limited range. For a correct accurate value of 8, it cannot give me 10 or 12. Then the computation will be completely jeopardized. But we can have some tolerance, and that is because of this massive data processing. We can have some kind of error tolerance in the hardware accelerator for MLAI. Now this become a problem when we try to create a detection method for approximate hardware. Okay, so how do we test hardware Trojan? Suppose I have an n input hardware circuit. Exhaustive enumeration might not be possible, but we take a large chunk of input and we test that whether the output is correct or not. Okay, but this hardware, if the Trojans are inserted in approximate adder, maintaining the error tolerance limit, then it's very hard to detect, right? So creating a hardware Trojan so that your error does not go beyond tolerance is also a challenge. So while designing hardware Trojan for approximate adders, the challenge is that the adversary can actually exploit natural inaccuracy in those approximate circuit to develop an attack methodology. So I will give a brief diagram. Don't get scared. So this is a basic approximate adder circuit. Okay, so what happens is that it's a k-bit addition. Okay, so sorry, no, it's a basically n k bits addition where every k bit is an accurate adder. Okay, but you imagine, suppose I have n k bit addition and the carry from the first block is going to the second block, then second block to third block. So by the time the nth block will come, it will only get activated after n minus 1th passing of the carry. Okay. So what approximate adder does, it predicts a carry. Okay. Now depending on the carry selection logic, it decides that whether I will wait for the real carry or I will go with the carry that I have predicted. So it's a probabilistic method, and that actually occurs some kind of error in the result. So this is how the block based low latency approximate adder looks like. So now how we are going to tamper it. Okay. So see, suppose this is a very small XOR gate. Okay. So what will happen if the circuit is fine, then for 0 and 1 0 I will get 1 1, otherwise I will get 0 0, right? It's a simple XOR gate. Now suppose my rare condition is whenever this C is 0, I will flip it to 1. That's only what I do as a hardware Trojan horse designer. So I will just add to check that whenever this C is 0, this not gate will flip it, and then this OR gate will do the rest, because it will always give you 1, and whether it is 0 or 1 does not matter, because it's an OR gate, it will always give 1. Okay. So this is a small hardware Trojan. If I want to flip the circuit whenever the C is 0, it's a simple example of hardware Trojan horse. Okay. Now what we do here, this is my full 1-bit adder. Please note the approximate adders are also made of full adder only, and I have just added this circuit over here. Now how my circuit will behave? So given A, B and C input, the S value should be look like this, and the C out should be look like this. Okay. Adding the hardware Trojan, whenever this S is 0, I am flipping it into 1. Okay. So this is how we insert a hardware Trojan in one of the full adder in the whole approximate adder circuit. Okay. NK bit approximate adder, I will just do just to add 2 gates, and it will actually devastate my design. Okay. So now which one full bit to replace, and how to ensure that the Trojan mask actually does not jeopardize, I mean it does not go beyond the error tolerance. So for that, since the tampered sum is always 1, so there is a possibility that 4 out of 8 times it will give wrong result. So the tester will find out, array, so this is wrong, it is very high probability, right? So now if the input carry is itself biased towards 1 with probability p, the final output will get biased with 1 by 2 to the power p, which is much less than 1. Okay. So what we do in the LSB side of the adder, we actually just add the Trojan. Okay. But we also do a hit and trial to give the input, get the output, and find out that exactly what position is best to insert the Trojan horse. Now this is the experiment that we have done. So for architecture like 8-bit, 16-bit and 32-bit, where there are number of blocks, that is k size is 4, we have found out that the first, second and 3 and 4th block can be tampered, and for these two the error will be bounded and application result will be affected. So but for this particular case, the application result will not be affected. So error is bounded, but the quality is degrading where I am using the approximate adder. Are you getting the problem? We have to insert the Trojan in such a way that it always remain in the tolerance level. Okay? But slowly it will decrease the quality of the application in which I am using the adder. Yes.
Just a quick, so what is the threat model here? So you need access, you're saying you need access to RTL itself to insert your...
I need an access in the Fab Lab. So I can get the RTL. Once I get the RTL, I can actually analyze it and put the hardware
So
Trojan.
let's say RTL is mostly encrypted, right? Even if they
Oh, there are ways to decrypt as well.
I see. So, but here the threat model is you need the RTL. to
Yeah,
insert this.
you know the RTL. You can reverse engineer the RTL, and then you just, while you are doing the fabrication, you just tweak a little bit.
But the error is injected during,
During not the gates are injected during fabrication.
during fabrication.
Yes. But it's so. But if you the advantage is that you do not you do not need the adder to be in your hand to understand that whether the error will be bounded or not. Okay, so you have probability value for that particular adder, that with this probability the prediction logic will be 0 and 1. If you know that, you can beforehand understand that which would be the best place to actually insert the Trojan. So as you can see that with untempered measures, these are all block based adders. The PSNR and the SSIM, which are the metric of to evaluate a certain application while we are running these designs for ML accelerators, they gets decreased for the tempered measures. Okay, but if you see that from the area power delay perspective, when we are fabricating, their values are very close to each other. See, 67.11 and 68.32. Okay, so if you see the area, the hardware Trojans actually incur very small area. That's why it passes the test. Okay, 5 minutes. I have just last topic to cover. So finally, the last topic, maybe I will not go to the detailed one, but I will just want to give you a brief of physically unclonable function. It's a hardware authentication. So what it does is that it creates a fingerprint of the device that can be used for device authentication through random number generators, IP protection and cryptographic protocol design. How does it do it? So what we do is that whenever we fabricate any chip, suppose we are fabricating a AND gate, okay. Now you give 0, 0, 0, 1, 1, 0, it will always give you 0, and if you give 1, 1, it will always give you 1. So the truth table is fixed, okay. But what is not fixed is how much time does it take to produce that output, okay, and it varies from chip to chip. So suppose for one particular AND gate it will take 5 nanosecond, the another can take 5.12 nanosecond. So this difference is called propagation delay, and this propagation delay happens due to the manufacturing defect while we are fabricating the chip. Physically unclonable function actually exploit this propagation delay to fingerprint a particular device. So what it does is we create a n stage symmetric layout, okay, using 2 cross 2 cross 1 multiplexer. So how does it work? At every stage I will give a selection value which is 0 or 1, and we will give a trigger, okay. So if the selection bit is 0, the trigger will go straight, otherwise they will cross the path. The idea is the delay to propagate from this point to this point, this point to this point, this point to this point, and this point to this point are different in the device, across the device. So what will happen? This trigger is always 1. One is passing in the upper layer, one is passing in the lower layer, but they will reach in the D flip-flop at 2 different time. So suppose this upper layer comes first, then the clock will not come by the time, right? Now when the clock arrives, then it will get a 1 value here and the response will be 1. And if clock comes first and yet the D value has not arrived, it will give us a 0. So then this circuit, the output or truth table of this circuit not only depends on these challenges but also on the hardware intrinsic property of this particular hardware. This is what we call as physically unclonable function, because you create the same circuit again and again, the propagation delays will be different. So if you have the truth table of a particular physically unclonable function, you cannot actually predict the truth table or the behavior of another physically unclonable function. So it sounds very fancy. So this is how actually we do take 2 cross 1 multiplexer and create the stages. And lastly it goes to the D flip-flop. Now again ML actually break our heart. So what it does is, suppose this path is called P path, R path, S path and Q path. These are the 4 paths, okay. So given the challenge, we can create a linear delay model of this architecture, okay. So every delay at the top and the bottom can be represented at the current path that is chosen, either it is P, Q and RS, the delay that is coming beforehand and the challenge that we are putting up. Okay. So ultimately what happens that the response of the final delay can be represented as a multiplication of the challenge as well as the delay. So even if we give a set of challenge and this responses for those challenge, the machine learning algorithm can find out this linear delay model and break your puff. Although it does not need to understand what are the exact delay that are there in all 4 stages and across the stages. Okay. So very bad news for hardware security engineers. So over the years we kept building resistance against machine learning attack to protect puff, and they kept breaking our design, and the machine learning is still breaking our designs. Okay. So so just I will show you one particular slide. So to protect the puff from the machine learning attacks, recently in TCAS1 a particular design has come up which has an inherent puff inside it. What it is doing, the challenge that we send, actually it goes to the puff and then the response is stored in a particular register. Okay. Now what we do, we give some separate challenge and we get the value, and from that we absorb the response that we have got, and the response from that we have got from this non-volatile memory, and this R comes out as a final response. So basically what we do, we obfuscate the challenge and obfuscate the response to stop the design from machine learning attacks. But in our paper, what we have shown is that the attacker actually can, I am not going into the details, you can refer to the paper, the attacker actually can intelligently select its challenge and get a response which is desired to actually feed into the machine learning tool, and this kind of critical design can also be broken by the machine learning attacks. So it's a huge area, people are still doing work on it. So the key takeaway for this part is that, I am not going on to all those details. So will strong puff can be completely discarded. So this delay puffs that we have just talked about are part of strong puff because it has 2 to the power n number of challenge response pair. You increase the challenge to n equals to 64 or 128, you will get a numerous number of challenges for authentication. But a machine learning attack is a great threat to that. So can we use machine learning to protect against machine learning attack? We actually working on this type of problems. And then there are few puff which are called weak puff that are generated from the SRAM memories and all. So can we actually, but that they are very hard to predict because they don't follow any linear delay model. So a lot of research work is currently happening on whether we can integrate weak puff and strong puff to merge for unlimited authentication without being compromised by machine learning attackers. So these are few things that we are doing in our lab, and yeah, that's the flavor just I wanted to give you about hardware security. Thank you for your patience, and I can, shall I thank or shall I ask question? Okay, so if you have any query, you can ask. Yes.
It's not exactly related to this.
Yeah.
But there have been cases where, let's say we are at a cafe or something, and there's a person on the table next to you. So to start the computer, they enter the password, right? So they can read the frequency changes in RAM. Later on, like we were talking about how the capacitor leads into vibrates the PCB. That's where you can track down the noise.
Yes.
But they do it with just like information being written off of and read from RAM. Yeah. So how are we even like what is the work that's being done to counter this?
Are you talking about key logging attacks?
Yeah, essentially, but it's more of like now it has come to a point wherein you can just do it with very minimal devices that to at like an open distance. Like for example, there could be so much noise. You're at a cafe, let's say, right? You're logging into your device, and with so much noise happening around, with all like a range of frequencies, this still can like zero down on you and kill all your attacks. So
the very popular thing that we do is doing obfuscation. There are a lot of obfuscation technique. When the data is going to the cache, we actually add some mask to that data. So the operation happens on the masked value, and we get the result.
But that has been there since years. But this was like a very recent attack.
So then can you tell? I mean, I am not aware of the thing that you are not talking about keylogging attack that I have understood.
Yeah.
But what exactly they exploit?
Essentially, they were able to like read the EM wave changes, and like when the data is being written into RAM and off of RAM, and using that they could like take away passwords.
Yeah. So
and the only way to prevent, like at least the article that was about it, the only way that they could
shielding it.
Yeah, in a Faraday cage.
Yeah.
So is there no other work to do?
No. So recently we are building up a setup where actually when the OTP comes up into the mobile mirror, right, they come from a ribbon from the screen controller to the screen basically. So those cable also emanates EM signal, and if you just capture them, they will tell you what OTP is coming to your mobile. For now, there is no countermeasure for such attacks.
Won't that aren't we leaving a whole bunch of devices to be vulnerable in the coming future?
True. But then we will be the one. We will get calls that, hello, this is the bank manager calling, please tell me your OTP, and we will tell the OTP. We don't need to even use the EM thing. So this is the cheaper router, we will buy it, and that router will not have any TLS layer.
No, to zero down my question, essentially
but yes, we need
an analogy to it is we understand that if quantum computers do become more common, we can break encryption systems such as RSA and all that. So there has been development in post-quantum encryption systems.
Yes.
Is there nothing like that being done with this, where we are accounting for these attacks?
As I said, one of the thing that the normal side channel countermeasure designers were doing is masking. This is the latest that we have done so far. But masking is very hard to implement in such kind of EM emanations when the data is passing through the bus or through the cable. This is very hard to do. But yeah, we have to look for it. But right now there is no countermeasure for such attacks. Yeah. One thing can be done that the moment it is coming to the but when we are doing in the keyboard, at least it first has to come to the processor. Then only the thing can be done. So that part, if that input to the register is insecure, then it's very hard to counter them.
Good afternoon, ma'am. My doubt is very specific. Like it is also offbeat to the topic, but it is very related to the topic.
Sure.
Recently in the news there was news about pager attacks in Israel or something like that.
Yeah.
So it was also something related to the malware, hardware trojans.
Yes.
My question is, given the complexity of network on chips and our daily mobile phones, if a pager can burst, then the complexity of mobile is too high, and it can give a greater impact also. So how can we, as individuals, reduce the impact? And my second question also translates very on similar lines.
Yes.
Since, for example, if you are talking about large learning models, not related to you, but it is related to the hardware security. So India doesn't have so many large learning models. The ChatGPT that we use, or whatever the AI tools that we are using, mostly they are maybe from Western countries or some other countries.
True.
So and the network architecture, the OSA layers, whatever the 7 layers, whatever we are using, except the application layer, all other 7 layers are belonging to Western countries, and maybe all other things are also the data centers also belong to the Western countries. So everything is, and we are talking about improvising the AI for them. So in future, if there is a situation like the pager attack, the impact is going to be very, very great, and all our data is all breached. So how are you going to?
No, I mean, see, right now government of India is taking a lot of strict step to defend hardware trojans. Okay, we are late, but we are doing it. A lot of mobile manufacturing companies are now shifting their fabrication lab from China to India. Samsung is one of them. So other than this, the problem is that we do not have any policy or standard right now in India to test hardware trojan. Many does not believe that hardware trojan attack can happen. So pager attack was one of the eye opener, I would say. And in IIT Kharagpur we have actually we have a hardware reverse engineering lab set up to understand whether there is a trojan. I think in IIT Madras they are also in collaboration with SETS. They are building up this kind of hardware reverse engineering laboratory where we can actually check whether there in a IC there is hardware trojan or not. But the effort has to be maybe multiplied to reach that level so that we can actually stop pager kind of attack.
Thank you.
Yeah. And for LLM, we do not need to go to hardware. There is already a lot of inference attack and other attacks. You just write a very intelligently made prompt into LLM and it will give you a lot of private information. So the attacker does not even need to go to hardware level. Any other question?
Yeah.
Yes.
Hi. So you said in the beginning of your talk, you mentioned about capacitor seaming. What is a possible countermeasure for capacitors? Because it's post-fabrication, you probably don't have a lot of room to make changes to the device. You said you would even isolate noise by removing other frequencies, right?
Yeah. So again, we can increase the noise, but up to certain level. Otherwise, the more the noise in the circuit, it will hamper the circuit component as well, right? So again, we can do some kind of obfuscation, which are done in few chips, Intel chips, I guess right now. For at least for EM to stop EM attack, they are doing some kind of power obfuscation. So other than that, I see.
But I think even power obfuscation, differential power attacks it'll make it harder, but not really eliminate.
Yeah, I mean, no countermeasure is foolproof. No countermeasure is foolproof. We just have to understand our root of trust, what we want to believe, and it's the more you will increase the security, your performance will degrade. So that it's always a compromise between performance and security. But to make the performance at the highest priority, jeopardizing the security overall, it's not a good idea. We have to make a trade-off between these two. At least in the hardware level, this is an issue.
Good afternoon. So as you mentioned regarding total 6 articles, 6 books, like as a CPU doctor and door knock attacks, timing attacks, timing side with channel attacks, and page attacks. So the last attribute puff.
Puff.
So that is a black puff also. So these are the articles as a representation of entire representation.
Yes.
So in this, my question is related to not attacks. So that is the first article related to CPU doctor.
Yes.
In the CPU doctor, as mentioned, is designed as a heartbeat sounds.
Yes.
That is acoustic signals point of view.
Yes.
So in that signals region, you mentioned is only 3 features.
No, I have said about 3 most significant features.
Okay.
So we actually run an MRMR algorithm and find out that these 3 contributes the more into the analysis. Yes.
That is related to MOCC. That is MOCC and ML filters and acoustic filters. There is 3 mentioned.
Yes.
Any other important major features regarding?
See, you know, there are a lot of inbuilt library in MATLAB.
Like Librosa and PyAudio. And,
So you explore them, you will get. There are total 7 features I remember. Three important features I have mentioned here.
Yes, ma'am.
Yeah.
So regarding, as mentioned regarding 2011 is mentioned one audio beat sounds. One data set also is there. So already I'm working on that particular data set. So in the particular data set, they were followed with 3 kind of many important.
You are working on acoustic side channels?
Yes, ma'am. Yes,
oh,
ma'am.
okay,
Yes,
good.
So that's the reason I asked to study for CPU data.
Okay, yeah. Tell me the question.
So not related to hardware point of view. It's a completely machine learning and deep learning point of view.
Okay.
So my question already you mentioned that is major features.
Yes,
But,
yes.
you are extracting the features of the major.
Yes.
So any other key points, ma'am, regarding for the extracting the features point of view?
One point that I don't know why you were using acoustic side channel, for what purpose, but you know, when we run this instructions, you know, we will get a overall signature, right? I think one of the more important point would be to cut these samples in a proper way, so that they don't get overlap with each other, and then do the analysis.
Yes, ma'am. So in that time we need to proceed segmentation.
Yes.
Yeah.
So you have to see and you have to understand that what is the nature in which the signatures are coming, and accordingly you have to cut and then do the analysis.
So depending on sample rate?
Yes, it will depend on the sample rate.
Okay.
So the frequency in which the phone or the computer is working, all those will be very important.
Yes, ma'am. Just now to see in the CPU doctor article also. As I mentioned, total 10 classifications. As a 10 classifications, as I mentioned with confusion matrix. Next one, as proceed with 8 classifications, and again proceed with 2 classifications also.
Yes.
So any data sets is mentioned, but sir.
No, we all we did with our own. I mean, we captured and then we did it.
How many number of patients are samples?
How many?
How many number of patients?
Sorry.
Patients are samples.
Patients.
Yeah, and heartbeat now.
Oh, no, it's heartbeat of the Arduino, not the patient. It's just, you know, you take one Arduino and start your, so we are not doing acoustic side channel on any real heart patient. We are just naming it in that way. So we are actually taking the heartbeat of the Arduino board. Okay, so you take the Arduino board, you run your assembly code, you just, you can have a, you know, acoustic gun as well. You do not need a stethoscope. With acoustic gun also you can collect the signature from far away and do the analysis.
Thank you.
Welcome, most welcome. Okay. No, it's all right. Any other question?
So let's end this.
Yes.
The hardware Trojan horses, right? So what is the state-of-the-art attack for the hardware Trojan horses? Like what has been demonstrated, let's say, on a commercial? I think barring the.
See, it is something you will not demonstrate. I am giving you a real example from a cab company. So I was doing PhD while in Kharagpur, and one of the famous cab company came to us. So they decided to create a dashboard in their car, which will take data from the sensor to understand for how long the driver is inside the seat and when he is not. Okay, so that they can understand that if he's saying that he is cancelling any request, he is at all in the car or not, or driving or not. We have found out that they have designed that data set and sent the design to China. When this dashboard came, there was a small chip like this. Whenever they were going to any public router or public Wi-Fi in Bangalore city, it was leaking information. So there, it is not even a gate, it's this size chip, and people were not able to find it. So no company will release that my device has been attacked by hardware Trojan.
There's some responsible disclosure or something, at least the software community did this.
This is, yeah, so you can understand the repercussion of this thing. For 4 years, those cars were in Bangalore city, and the data of the people who were actually riding in those cars were leaking out to China. So
This is not in public domain.
no. They came to us that what we can do, but this is a real experience that I had with hardware Trojan.
But they eventually found out data leak was happening.
Yes, and it was not through any malware or something. It was just through that small modem that was there.
Is there any more questions? Let's finally thank you.
No, but I'm very happy that people has asked so many questions. I mean, they have listened to it. I'm very grateful. Thank you so much.
So we have a small.
And good afternoon to all of you. So first let me set your minds at rest. Professor Chatterjee made a convincing case that there was information being leaked about Bangalore roads, right? There is only one information you'll get. You're stuck on the road in traffic. That's it. So I'm sure the Chinese must be bored by now, saying that where are these guys to? Okay. But she also made a very lucid and captivating talk about how you can have side channel attacks. You brought in singing capacitors, you brought in chattering timers, you had Trojan horses and so on. But to mount those attacks requires quite some sophistication. We leave that to the Israelis. In India, we like cheap things, quick things. So you might be asking, I want to attack my university. That's the obvious thing I want to do. Because rather than studying for the courses, just go and change the grades, right? That's a smart way of doing it. Especially if you're a CS student, that's the challenge. So if you want to do that, are there easier ways to attack systems? And the good news is yes. You can attack them through database systems, because database systems are what is the repository of all relevant information within your university or any corporation or institution or enterprise. And let's attack the database system itself. So what I'll try to do in this talk is to show you how database systems get attacked, and are there mechanisms by which we can try to prevent these attacks and identify them before they cause serious harm to your system. Okay? So we will look at, specifically the problem that we'll also look at is, how do you do this non-invasively? Okay? Right, where basically you have a black box and you're trying to figure out what is there in the black box, and that's why you have this anime picture that you see here. You're trying to figure out what is there in a black box without opening the box. Okay? But just by looking at its behavior. Okay, so just to set the stage, I'm sure, hopefully most of you would have done some undergraduate course in database systems or data storage and so on. So you would know that the intergalactic standard for storing information in today's enterprises is what is called as a relational database system. And this is just a fancy term for saying that all your data is going to be stored in a variety of tables. Okay? So for example, here you have a very simple university database where you have students, and then they have roll numbers, names and addresses. Then you have courses, where you have the course number, the title of the course, and how many credits you get for completing the course. And then there's a register table which connects up this to information by saying that this particular student has registered for this particular course and you have gotten this particular grade. Okay? So everything is just in a set of tables. And the way to access information within this set of tables is what is called as the structured query language. Okay? It's actually not very structured, but that's the name that it was given to it in 1970s. All these systems essentially came from the IBM research labs in the 70s and 80s. That was the fount of all database knowledge in those times. So this is the structured query language, also known as SQL or SQL, depending on what pronunciation like. And let's assume that, for example, here, your vice chancellor wants to pull out the names of the students and their courses. Okay? They want to find out what kinds of courses are students taking. Beyond AI and ML, are they also taking databases or not, right? That's important. So you can express it in the syntax that you see here, where basically it says that select the name of the student, that is the one coming from here, and the title from the course table here. And then where do you get this information from? You have to combine, you have to take these three tables, student, course, and register, because this is the repository of the information that you have to extract. And then you have to connect them up meaningfully. And that's what you see in the last two predicates here. It says where the roll number here should match with the roll number here. Only then you would output the name. And similarly here, the course number here should match with the course number here. This is the predicate that you are trying to assign to ensure that there is some relevant meaningfulness in terms of the information that you are producing. So this is all that you need to know about the structured query language. This is the standard interface to extract information from relational databases. And pretty much, if you've used an Oracle system, or you've used IBM's DB2, or you've used SQL Server from Microsoft, or if you use Postgres, any of these systems, they are all relational database systems in one form or the other. Okay? And they all have these kinds of interfaces. Okay, so now let's come to the more interesting part. Okay? Don't need to have all these sophisticated things where you have to actually go to the fab and go and change things and put in these additional gates. Just mount an SQL injection attack. Okay? And I don't want you to be taken literally, because earlier the heartbeat was taken literally to be a patient. This injection is not the injection that you're going to do this year. This is an injection of this here. Yeah. This is a code insertion technique. Okay. Pretty nice. This is a code insertion technique to attack applications. And basically what is happening is that attackers insert SQL statements like the one that you saw in the previous slide into the application fields. And you can do this there's lots of different ways or platforms through which you can do this insertion. You can do it via software tools, or you can do it via scripting engines, or through the browser itself. And why do you want to do this? Of course, there are very good reasons. You want to spoof your identity, or you want to steal the data, or you want to change it. Okay, this is particularly important if you want to change your grades. Okay, change all the F's to A's and so on. And then you also want to do something even more dangerous, is to change the access permissions themselves. Because you want to find out what are the grades of your instructors when they took the courses, right? That's even more interesting to know. And this is actually the most pernicious vulnerability in computing today. Okay? Very few people have except in IIT Kharagpur, know how to go and attack a side channel attack. Okay? This one, everybody and the grandmother can do it, sitting right here. So this is responsible for the most of the successful hacking related data breaches that you have today. Okay? You might be wondering, okay, how come this is still going on? People have been seeing this for a long time, but repeatedly you will see that a certain enterprise much of its data has become public. It's being sold in the Majestic bus stand here by the Bush and Lords in the MBs, right? So in fact, if you look at web applications, they are being attacked regularly because you have these automated tools which keep trying it all the time. And you keep saying that someday or the other you'll have made a mistake and I can break through into your system. So there are hundreds of attacks per hour, and they don't require much sophistication to do it. So you might say, okay, I'm an ML person. I can get signatures and then figure it out. But there are easy ways to circumvent this. Okay, even the hackers today are pretty smart and so on. Okay? This can be easily circumvented, and there are attack tools already available for you. Okay? You can download them. You don't have to put it in a Faraday cage and all that. Just download the software and run it. It will work. It's called SQL Map, and then Hawij is very popular. It's from Iran, so must be good. Right? They know how to protect the system. So, where do these attacks occur? This pie chart actually shows you that it gives you across different domains where the SQL injection attacks are occurring. As you will see, about 15% is against the government. Okay? That's always a fruitful exercise. Health, another 15%. Okay? News, 12%. In today's world, this is extremely important. Okay? finance 11%, and so on. So pretty much across the board. And education 7%, okay? Some of them are here, right? So you can see that this is a very widespread across many different domains that these SQL injection attacks are occurring. Now, who are mounting the attacks, right? That's what is shown in this graph here. Here it shows the attacking country, or where the attacker is from, and this shows the attacked country. Okay? So if you look at the diagonal, it means that you're attacking within your own country. And that obviously is going to be much more likely because you want to attack your friends, right? Who wants to attack remote enemies? Okay? You want to attack your project partners in your courses and stuff. So you'll see that this is usually the maximum. But what is interesting is that let's look at India here. Okay? So India, although we're supposed to be a non-violent country, we do mount attacks. Right? And where are we mounting the attacks? You can see in this channel, the column here, 60 attacks from within the country itself. But we don't spare others as well. 11 against France. Canada is 5. This will probably increase in a few years. 5 here, Japan, and 5 against the US. And similarly, if you look at this row here, where the recipient is located in India, you can see that there's a healthy number of people who are interested in what you guys are doing here. So the point is that both from an attacking perspective and being attacked, you have a good representation. Okay. So now you might say that if the SQL query was coming in plain text, you could look at it and say that this is going to be dangerous for your health, therefore don't admit it into the system. Okay? But then we have all these crypto people we just saw in the previous talks. You can make the query to become essentially invisible. Invisible in the sense that you can do encryption, which is one obvious way. Other is to also do obfuscation, which was talked about in the previous session, where you can actually put in a lot of junk around the query that you have, such that it's hard to make out what the query is actually doing. Okay? This we routinely do in our programming code. Okay? Very few of us can figure out what the previous guy did, especially if in the industry you would have said, the previous guy wrote code, nobody can understand it. So you don't want to touch it, right? But even if you don't do this naturally, you can do this deliberately, and I'll show you an example of this later. Or what is even more interesting is that if you look at the SQL language, the reason that it is so popular is that it's what is called as a declarative language. That is, you only specify the target that you want without specifying the means to achieve the target. So if you remember the earlier query we had, we just said that give me the names of the students and their courses, and this is how you connect the information. We didn't tell you exactly how to go through the process of doing those connections. Whereas in your regular programming, which is called as imperative programming or procedural programming, you have to give every step of the way. So if you're going to invert a matrix, you have to go and say every step what has to be done, all the lines of code have to be written down by you, and you have to give the full specifications. The beauty of SQL is it just says give me the target, I'll go and figure out how to achieve it. But what might happen is often in industries, people are too lazy to learn SQL, so they go and write actually procedural or imperative code, and this can be arbitrarily dense. So it's very hard to figure out that what you're doing is actually malicious just by looking at what is given within the program. Okay, so here is a simple example. Okay, that let's say you say I want to select star from the passwords file. That is basically attacking the passwords file, and you want it. And as I said earlier, usually these things are already public domain, but you are hoping that it's currently kept secret. So you want to select star from passwords. You don't want to write it in an obvious way. Instead, you can do encryption like what you see here, which is essentially the hex encoding of this statement here. So now what happens is that eventually the database engine has to be able to do a decryption of this encoded query because it needs to execute it. And that's certainly true at the very last step, you will get to know what the query is. But ideally, it's like suppose somebody wants to attack your house. Okay, one choice is to stop them at the front gate itself. The next choice is to stop it at your front door. The third choice is to stop it at your bathroom door where you're hiding. Right? These are the 3 layers. Eventually you're stopping, right? But you would have liked to have stopped it at the gate to your house itself and not at the second or third line of defense. Okay? So here also, ultimately you would be able to recognize it, but the danger is that it's already well deep into the system, which means that it could have side effects and side attacks and so on. The second worry is that if your internal engine has to worry about the fact that whether a query is good or malicious, then it's going to spend a lot of time in figuring this out. And that will slow down the normal processing because as Professor Chatterjee said, you always have this dichotomy between security and performance. Now, if you are going to start looking deep inside your engine about the security aspects, your performance will naturally suffer. So ideally, you want to stop people at your gate to your house and not inside the front door or the bedroom door or whatever. So this is what we would like to figure out. So as I said, one is encryption. The other option is to do what's called as obfuscation. So this is actually an SQL query. And so those of you who are familiar with it will see that there are lots of complicated statements here, including things like the select the value 1 and so on. Actually, this is an aggregation which is being done by basically counting 1 a certain number of times. But if you take this complex structure, it's actually can be reduced to this much simpler version of the same query, semantically identical, but it's very hard to look at this and figure out this is actually what you're doing. So you can throw in a lot of junk to camouflage what you're really trying to do, and it's very hard for a third party to go and figure out that internally you have a malicious intent, but that is now coming under this garb of a query which is hard to understand. So the question that we asked is that how do you extract these opaque SQL queries that are embedded within the application, but they are hidden under either mathematics, like if you're going to do encryption, or hidden under software by doing obfuscation tools. And incidentally, if you look at most of your Android apps, there's a deliberate obfuscation being done because you want to protect the intellectual property. So there's also a goodness about obfuscation is you don't want somebody to steal your intellectual property of the great app that you developed and use it somewhere else. So they deliberately throw in a lot of useless code. Okay? But in this case, this can be used for malicious intent to hide the fact that you're actually doing something dangerous to the system. Okay. So now you have two ways to do it. Okay? Continuing on the medical analogies, you can use forensic techniques. Okay? You can do a post-mortem of the code, get the binary file, open the A dot out, do all the binary OD minus BC kind of commands and so on. If you do all that, you would be able to succeed to some extent to figure out what the queries are if the strings were present in the original framework itself. So you had a SQL string which had been converted to binary. You can use string extraction tools which are quite common from the object code itself. Or you can also go deep inside your engine and look at the what's called as the execution plan, because remember we said that the beauty of SQL is you only give the goals, you don't supply the means to the end, and somewhere somebody has to figure out the means. And when you look at the means, you can figure out what the query is doing. But the problem is that many of the encryption tools that we have today, these are meant for good purposes because you as the person may not want other people to see your queries. Example, SQL Shield is very popular with the Microsoft SQL Server product. They hide all these structures. They hide the query logs, they hide the query execution plans, and it's only the very last step that gets exposed to the database engine. Also nowadays, this is fine for on-prem kinds of environments, but if you have things on the cloud, you'll not even be able to go and ask to see all these internal details because that won't be given to you by the cloud provider. Okay? So why are you asking all this stuff? Okay? Why do you want to come inside here? So the database internals may be inaccessible on remote platforms. And then for each of the specific platforms or apps that you have to come up now with customized solutions to be able to understand the binary code that was there. And what is worst is that if the code was not written in SQL, then it won't be in strings format. It will be in actual binary code. You may have the equivalent of the SQL written in, so the declarative code can be rewritten in imperative or procedural code. You will never be able to figure this out here. Okay? So applying a heavy duty or heavyweight kind of attack weapon on this is going to be counterproductive because it's going to be largely not usable in most circumstances. So instead, what we did is to say that can we use some non-invasive techniques to figure out what is lurking underneath the surface. Okay? So I'm sure all of you have seen these movies, right? I know what you did last summer. I know what you did last 2 summers and so on. Okay? So this is what we want to know. What is there underneath it? Okay? And do this non-invasive. So we would like to learn the query ideally from just looking at input and output examples. Okay? When we started this project, we were honest to goodness database people. We said, yeah, input and output examples. Later I found that it helps sell your paper if you attach some machine learning to it. So I went and looked at what machine learning matches with this. Said active learning. So it sounds good, okay? It's like boost.bonvita, active learning. So active learning means that you don't have a kind of predefined training set. You keep changing your training set based on the outputs that you saw on the earlier training set you did. So essentially it's a feedback loop. Okay, so the nice thing, and I'll show you how you can actually do this pretty well. The nice thing is now you don't care about the platform or the application because you're not looking inside. You're just saying, tell me how you behave. And based on your behavior, I can tell you what is inside your DNA. This is also extremely lightweight now. It doesn't matter whether it is SQL code or whether it is C++ or whether it's Java or Python. Because again, we're not opening the box. If you're not opening the box, I'm impervious to or agnostic to how you have written it in the first place. Of course, on the downside, you cannot handle all queries that the previous forensic techniques could have handled. There's some limitations on scope and so on. I'll come back to this later on. And also there are certain kinds of impossibilities where you cannot figure out certain things. But largely these impossibilities are not very semantically meaningful, so we'll ignore that for now. Okay? But what I want to point out is that, especially because most of you folks think that life started after the year 2000, right? Now we might say active learning today with ML, AI, foundation models, all this and so on. Machine learning was there in the Second World War. Okay? And let me show an example of where active learning was actually used. And this is the reason that today you're eating pizza and not sushi. Okay? So this is really the case. So this is the famous Battle of Midway, which happened in June 1942, which for those of you who read the history and remember it from your high school days, was about 6-7 months after Pearl Harbor. And in Pearl Harbor, essentially, the majority of the US naval fleet had been destroyed while it was anchored itself because they had not expected that attack. And 2/3 of their capital ships had been wiped out in that December of 1941. So now the Americans knew that the Japanese wanted to come and give essentially the killer blow and remove the remaining 1/3 as well. Okay? And why is it important to remove that? Because here you have this huge Pacific Ocean. This is the US here, along with San Diego is here, which is the home of the naval fleet from here. This is Japan here. And basically, in Hawaii here, in the Pearl Harbor, they had done the attack in 1941. So now they said that let's finish this, guys. Okay, we did 2/3 last time. Let's take the remaining 1/3. And it was no surprise, the Americans also knew the attack was coming. But the Pacific Ocean is quite large. Okay? It's almost as large as the lake in Hebal nowadays, right? With the water flowing everywhere. Yes, it's pretty large here. You don't know where the attack is coming. You know it's going to come, but you don't know where. And if you do make the wrong estimation or prediction where it is, you're going to be in deep trouble. Okay? Because they'd already had it decimated. And now if you find that you've spread your forces too thin, you'll of course go and lose all the information, all the ships that you had remaining. So this was Admiral Yamamoto, who was the chief of the Japanese general staff, the naval staff here. And they said that let's go and attack these Americans again. And the Americans were in deep trouble because, as I said, they couldn't figure out where the attack would occur here. Okay? So they did a very interesting thing. They used active learning. Okay? They didn't call it that. So the Americans knew, because they were monitoring all this radio traffic, I mean, like we saw earlier itself, right? Everything gets monitored, all frequencies, all EM waves, everything was getting monitored. They knew the attack was coming, but it was codenamed as AF. Okay? So you know that the attack is going to be in AF, but you don't know what AF is. Okay? And we have a large Pacific Ocean. Where the hell is the AF coming from? So they thought it might be Midway Island, which is actually the island that you see here, which is almost exactly midway between Japan and US here. Okay? They thought it might be that, but couldn't be sure. And if you make a mistake, as I said, you might have seen, some of you guys might have seen this art history series where they actually, Germany wins the Second World War and Japan takes the Pacific side of the US and Germany takes the eastern side. Okay, I think it's called In High Places or something like that. I forget the full name. Yeah? Man in the High Castle. Yeah, Man in the High. Okay. So some people at least watching Netflix along with me. Good to see that. Please watch Netflix. Right. Yeah. So that's a very interesting historical thing, saying that what if they had won? Okay. How would life have been? Okay. So now the Americans think it is this, but they cannot be sure. as to whether it's Midway Island or not. They just know the code AF. So what they did was they sent out a fake message. And this was done in the essentially the clear text in a radio message saying that my water plant has broken down. This is like the calls you get from Maneta Tech Park, right? So, water plant had broken down. You don't have to encode this. Within 24 hours, they picked up the Japanese naval traffic, which they were monitoring, but of course was all encrypted and so on. And Japanese radio traffic said, AF is short on water. So now they could immediately make the connection that AF was actually Midway Island. And because they knew this, they were able to assemble their ships in advance. The Japanese didn't know what came and hit them. This is actually the entire Japanese aircraft carrier fleet. Okay? All the capital ships were completely destroyed. And this is the most stunning and decisive blow in the history of naval warfare. And that's because of active learning. Okay, just figure things out. So as I said today, if you're eating pizza, it's because of this. Otherwise you would have been eating sushi instead. That's it. Okay, so this was a very long story to come to what I actually wanted to tell you, is that now what we want to do is to extract queries from binary applications. These are essentially coded applications where you only have the object code and you want to figure out what's inside without actually forensically trying to open it up. So given an opaque application, which is called as E, it contains a hidden SQL query. So this Q sub H, so it refers to it being hidden. And you have some database instance on which this query produces a result. Okay? It doesn't matter what this instance is, as long as it produces a non-zero result. Now our goal is to non-invasively essentially unmask the hidden query to reveal what was the original query inside the application. That's our goal. And notice that the hidden query can either be actually SQL itself, or it could be its equivalent in imperative or procedural code. It doesn't matter, and we won't even know. There is no restriction on what is the contents of the initial instance of the database or result. We're just saying, give me some database on which it produces a non-zero result. And the reason that we just require this is, otherwise we would have to keep doing trial and error database generation to figure out some database on which this query produces an answer, and that is potentially may not, it could take arbitrary amounts of time. Okay? And what is important is, we are going to be non-invasive with respect to the application, but not with respect to the database. So think of yourself, you are the database server, you are worried about injection attacks coming to you, and I want to mount at the front gate of my house, I want to check what are the antecedents of this query, what are its intentions, even though it may have come in an obfuscated way, or it could have come in imperative code, or it could come in encrypted format. I want to know what you are doing. If it's coming from a Russian IP address, I certainly want to check, right? Okay, so these are the rules of the game now. User gives you this application, which is encrypted in some way or the other. The database schema, which is all the tables and the attributes of the different tables that you have and the data types, as well as various kinds of integrity constraints, that's given to you. And this some database, again, we don't care about the identity, which produces a non-zero answer. That's all that is given to you by the user. And you as the extractor can go and make a complete copy of your own database, or this database that was given to you, this instance. You can remove all the constraints because you are doing this on the side. And you're also allowed to repeatedly run this user application on top of the database that you have created. Okay? And all that you are allowed to do is that you can run this application on database and you can only look at the output. So you can only do inputs and outputs, but you cannot open the box. Okay. So now, why was this considered hard? At the time we started this project, everybody felt that this was a pointless exercise. Okay, and I was told by some senior database people also saying, why are you wasting your time on this? Okay? Of course, we had become good at wasting our time, so we said, okay, let's continue to do this. But they said, why do you want to do it? Because it's going to be hard. And why is it hard? It's because there are lots of dependencies between the various parts of an SQL query. As I'll show you in the next slide, everything is interconnected. Everything is correlated. Okay? So there are the different clauses, like example, like filter predicates and grouping and so on. All of them have connections to each other. You can also do renaming of the results of the query in the sense that the output columns may have new names that have no relevance to the original names. You are also going to take this data and you are going to budgie it in many different ways. You can do aggregation functions which do the sum or the count or the average and things like this. And you may also have arbitrary scalar functions, which are called as computed column functions, which would just give you numbers at the output of your query. So when we started, the expectation was that you can only do very trivial stuff. Trivial stuff like saying select name from students, okay, which one could do essentially in a very trivial way. Only such queries you could handle, but any query of reasonable complexity, because of the fact that all these interactions are happening, you would always be confused and you won't know what is inside. But the good news is that, and I should also admit here, I also thought that we could only get very so far. But I said, let's waste the time of a few students here. Let's go a little further and see how far can you go. Okay, you don't have much to do. Okay, Netflix, you have finished all the series. Okay, Man in High Castle done. What do you want to do? Let's try something challenging and see how far can you take this. And to my own pleasant surprise, we have been able to actually take it very far, much further than anybody expected, including me, as I said. Okay, so let's take a hidden query that you see here. So again, you will see that in most database queries, there will be a select statement, from statement, where, grouping in order. Even if you're not familiar with SQL, it doesn't matter. But this is a fairly complicated query, which is part of the industrial strength benchmarks. It's called TPCH, which is Transaction Processing Council. This is an independent benchmark on which most commercial database systems evaluate their performance. And you have done this with encryption here. And if you look at this query, it has lots of complexities. For example, it has what's called as a predicate on the dates, that the order date should be less than 15th March 1995. Ship date should be greater than the same date. There is a predicate on the string. It says that the market segment for this customer should be building. There should be multiple joint predicates, which is combining the tables. And then you see there are 3 tables here. Okay? And then you see there is multiple attributes on which grouping is being done. There is also an ordering requirement saying that when the output is produced, I want it in a certain order. All this is there. Okay? A limit function tells you how many rows of the output do I want. I may get 1,000,000 rows, but I only want the top 10. And then here, as you can see, this is what is actually being produced as the output table. It has information like the order key, but then it also has this complicated function which says extended price into 1 minus L discount. Okay, this is like computing your GST. Okay. The date, ship priority, and there's an aggregate function somewhere. Okay. This is the kind of query which is a fairly complicated query, usually run on large database, petabyte-sized warehouses. And it would be assumed that it's going to be extremely difficult to figure out that this is what is sitting under the hood. But actually what is surprising is we can do this. Okay? We can do this to the extent that this query that we produce will be semantically identical to this here. What would be different, maybe some amount of syntax. Okay? So for example, let me just show that to you here. If you look at this grouping set of attributes, this is a set of attributes. It's not a sequence, but a set. It's basically saying that I want equality on all these 3 attributes for all the people in the same group. It doesn't matter which order you give them in. Because it don't matter order, I may get a different order here, then a different ordering here, but still the semantics are the same. You might also see that, one other difference here is that this says less than 15th March 1995, this says less than or equal to 14th March 1995. Okay? Notice that not even God could figure out the difference between these two because they're identical mathematically. So there is no way that one could distinguish whether it was this or this. And what is more important, it doesn't matter. Right? You are looking at what is the semantics of the query. So whether I wrote it as less than or equal to 14th March or less than 15th March is identical. So this is what you are actually able to do. So now what's the magic behind the scenes? Is that we use what is called as database mutation techniques and database generation techniques to be able to expose this hidden query which is sitting inside the binary file. Okay? So what we do is that we first create a template query because we know that all SQL queries look like this. So notice that we are not doing arbitrary programs. That's much harder. SQL is not a Turing complete language. Okay? It has a very fixed structure and the structure is always going to be like this here. Okay? Select, from, where, grouping, order and limit. Okay? So this is usually called as SPJGAOL. That's the kind of name for it. And what we do is we create a template query where all of these things that you see in the colored regions here are essentially the fields that you need to fill in here. So P is the projection attributes, A is the aggregation fields that you have, from tells you the set of tables that you're going to access in order to retrieve the information for this particular query. These are the join conditions and filter conditions here, grouping attributes, ordering, limit, and so. Okay? So we create a template query like this, and we are going to extract each of these clauses separately and essentially paste them all together. Okay, so we always need to have, in order to again sell your research, very important to have a good name for it. Okay, even if the research is horrible, the name should be good. Okay, that's critical. Okay? So we had this thing called Unmask, which has a fairly labored expansion here. Unified non-invasive machine for SQL query extraction. Okay, kind of works. Okay, that's it. Yeah. Okay, so maybe let me skip this one. How do we do this design? So this is a pipeline which has actually two segments in it. The input to it is your opaque executable, which is the binary file, and this sample database on which this executable will produce a non-zero result. And then we pass it through our database mutation pipeline. The first thing is to say, what are the tables relevant to this query? Because typically you'll have hundreds of tables in a database. Your query may be only looking at information in a few of those tables. Okay? So you want to know which tables are present. Next is that we do what's called as a database minimization step. Okay, so the tricky part here is that suppose your original database that you had was a petabyte. And now you say, I keep running the application repeatedly on this petabyte. Then you will have to wait for your grandchildren to be born before you can come and get the answer. You'll eventually get it saying, I found the hidden query. But by that time, the world will probably have ended, right? So it doesn't make a difference. So you need to do this fast as well. You're going to run the application hundreds of times, and it has to be done fast. So you want to make this database as chota as possible. Otherwise, you'll be continuously doing this petabyte database operations, which will never get completed. So there's a minimization step here. Next is you want to pull out different pieces of the query. And it's very important that you do it in a particular sequence. You cannot do it in an arbitrary sequence. So first you need to pull out what are called as the join predicates. That is where two tables are being connected to each other. Then you need to pull out all the filter predicates where you are putting restrictions on the values that are acceptable in columns. Then you come to the projection attributes, that is the attributes that are going to be there in the final output table that you're producing, the result table. Then you also need to extract the grouping, and so this is the what's called as the mutation pipeline. Then we come to a database generation pipeline where we create synthetic databases, which are again very small. Okay? None of our databases and what we produce will be more than 10 rows. Okay? It's the world's tiniest databases that you have. So you create synthetic databases from which you can extract the grouping, aggregation, ordering, limit, and stuff like this. Okay? So I will just cover a few techniques here so that you get the flavor of how this can be done. You can I can give you some references later for the overall scheme as to how we do this, as well as some extensions to what we have done beyond what is shown here. So we can do that at the end of the talk. But let's just see what we can do by just some simple mutation techniques. Okay? So let's assume that your initial database was your typical university database again, student, course, and enrollment or registration here, and then there's a faculty table here. When you run this application, which is opaque, on this table, it produces two outputs. It produces a table with two columns, name and score, and these are some values that you produce here. So basically, this is the input database, which could be an arbitrary database, as long as it produces a non-zero result here. Okay? We are not putting any other restrictions. Okay? Just a Boolean requirement. Empty, khali or not. Okay? If it's not khali, we're done. Okay, so this is what we have. In this mutation pipeline, I need to first figure out which tables are relevant. So we do a very cheap trick. What we say is, go and take the student table and change it into a name that exists outside of the database system. Right? Okay? Just call it old student or something like that. If you do that, and this SQL, this application is run against the database, the first thing the database engine would do, because it's not a particularly pleasant error messages, it'll say, what the hell, I don't have an old students table. Okay? So when you do that, it tells you then that basically that the students table whose name you had changed is actually part of this query. That's why it's complaining. But if there was some other table, okay, let's say there was something about the hostels, which is not relevant to this particular query, then despite your renaming that table, there won't be any change in terms of the impact of this query when it runs. It will say, fine, the tables I want are all there. If you change the names of other tables, I don't care. Right? So to verify whether a particular table is present inside this hidden query or not, temporarily do a renaming to something which is outside the legal set that you have. Run it on this mutated schema, so to speak. If it throws an error, you know that it's part of the hidden query, and then you revert the name to this original name. And you do this in essentially a linear fashion across all the tables. And this can be pretty fast, because database systems are very good at saying, no, I don't want to do anything. Okay, they're very quick. Okay? Say, your tables itself are not there. Good, I don't have to do work. Okay? Only if you put a gun to the head, they'll say, okay, forcing me, I'll have to do it. So they're very keen to find errors. And this is like what you see in most of academic sections in universities, right? Moment you go there, say, did you bring 3 copies of Aadhaar card? No. Okay, did you get this? They want to send you back as quickly as possible. Database systems are like that. Yeah? Okay, so here we can figure out that in this particular query, student, enroll, and course are relevant. Faculty we know are optional. They're not particularly useful guys, right? So faculty is not part of this query. You're not bothered about it. Okay, so this is the start part. Next is how to do minimization of the database. So what I want to do is, given this initial database instance and this opaque executable producing this non-zero result, I want to derive a smaller version of this database such that if I removed any row from this minimized version, it will immediately transition to a Kali result. Okay? So this is the most simplest version of the database, and if you try to make it any simpler, you'll get no output. Okay? So what is interesting is that you can actually show that for the kinds of queries that we are considering here, which is this SPJGAOL, which I was referring to earlier, there always exists a minimized database, and this is as minimum as you can get. It has only 1 row per table. Okay? So you can prove that every single table will have only a single row left, which means that you have taken your petabyte database and converted it into the skinniest version of it, where essentially there is only 1 row per table. How do you do this computation? You can do an easy recursive partitioning of the database, where you take the tables, take the biggest table, chop it in half, run the executable. If it produces an answer, you can throw away the other half. If it doesn't produce an answer, then you keep the other half, because either one of them must be useful for producing the answer. Right? So it's a very simple technique, and I'll just show that to you through example here. Initially, you had about 5 rows in student, 2 rows in course, and another 6 rows here in enroll. This is what you started with. What I'll do is I'll take my biggest table here, which has 6 rows. I'll cut it arbitrarily in half. Okay? So I'll do that here. What I see is that after I cut it in half, these values changed. But I don't care. I just want a populated result. I'm not interested in the antecedents and the values and the numbers and so on. Just make sure it's not empty. Okay? That's the thing. So this is what you got here. Then you take this table, which is now the largest. Again, break it roughly into 2. So if you do this, you'll find that again you're getting a populated answer. The values are changing, but still there are rows in the output table. So you keep doing this until you finally come to a situation where these 3 rows, there's 1 per table, are still producing this output here, which means that we are now reached a stage where the large original database has come to a single row, which means that if I run my application even hundreds or thousands of times on this, it's going to be lightning fast, because it will run in picoseconds, right? So in that sense, this is a critical step to make this practical. Okay, so this seems to be a security person, message preview hidden. Okay. Right, so, yeah, so this is how you can do it. Okay, now let me just look at how to quickly show you how to do, or how much time is left, Sumit? Or 2 minutes? Is it? Oh, okay. Then okay, maybe I just skip this, the join part. I'll just show you the filter part, which should be easier. Otherwise, it takes a little time. So we had that earlier set of 3 rows, and we said that produces useful result. So what I will do is, I'll go and check, are there any restrictions on saying that, for example, age should be greater than 50, or name should be less than Jayant, or something like that. If I want to check, I'll take each of the columns, and in the minimized database, where we had essentially 1 row per table, that's why we call this as D superscript 1, which means there's 1 row per table. that is coming from a data type which has a minimum value and a maximum value. So for example, if you look at positive numbers from 0 to 2 power 64, for example, right? So I'll replace the value k for that particular attribute. So I'll replace, for example, age of 25 that was there. I'll replace it the lowest value, which could be 0. And again execute this opaque application, and I will get some result. Similarly, I replace it with the maximum of the domain, which could be, let's say, 10,000 that I use for age. I use it maximum here and again execute it. Now, based on the size of the results, okay, that is R1 and R2 the results, and we're checking whether R1 and R2 are Kali or not. Okay. If they are, neither of them is empty, which means no here. Okay, this is checking for emptiness. If neither of them are empty, it means that you have no restriction on that attribute. You don't care what the value is. But if you find that when you put it to the lowest value, you said yes, that I'm no longer able to produce a populated output, then it means that there is a left-handed limit on the range that's being applied. So you're saying that age should be, for example, greater than 20 or some number like that. Similarly, if you get it on the for R2, it means that you're having a right-sided limit. And if you get an empty result for both of them, for both Imin and Imax, it means you have a double-sided range predicate, which means that you have essentially lower limit less than the attribute, less than the higher limit. So you're having a predicate saying age should be between, let's say, 20 to 60. Okay? You're looking for senior citizens and pushing them out, so you want to do 20 to 60. Find L and R. Okay, so once you do this, let's say in this particular case, I put the credits as being equal to 0 here, which is the lower limit here. I will get that the output becomes Kali. Whereas when I put the maximum value of credits in the course table, which is 20, then it's no longer empty, which means that this is a one-sided predicate, which matches with this row that you have here. So I know that there is a left limit, but there's no upper bound. So there's a lower bound, but no upper bound. I need to find the lower bound. How do I do that? Very trivially, you can do a binary search on this value from Imin to the value k that you had here. It should be somewhere between these two ranges, and therefore you can get the value. In this case, it happens to be 2. Okay? Yeah, so this is how you can do all of this. And since we are run out of time, I'll skip this part. I'll just show this to you, that does this work well. So we have done this on the well-known industrial strength benchmarks, which are all very well accepted by the general community at large. And you can see these are different queries that come from the benchmark, so don't worry about what they are. They are different. There are 22 queries in the benchmark, so that goes from Q1 to Q21. What is important is the time. That does it take ages to complete the extraction of these queries? And what is interesting to see here, no, you can do it in a few minutes. And this is an offline process. If somebody has come to the front gate, you are saying, show me your camera, show me your Aadhaar card, get me your PAN number, right? That's what we do nowadays. Yeah. DG Yatra, is it there? No, everything you are checking. So at the front gate you are checking. If it takes 10 minutes to find out a dangerous query, it's well worth your time. Okay? Anyway, it's the user who's waiting. Okay? The server is not getting affected by it. You can also do this on other benchmarks called TPC-DS, which is again a large warehousing environment. Few minutes you can complete it. So what is nice is that all the extractions are completed in reasonable time. And you might say, okay, did you really run the executable many times? It's actually you run it hundreds of times. But because we are running it on these tiny databases with just one row, almost pathetic, right? One row per table, you can run it hundreds of times, keep looking at inputs and outputs, figuring out if you poke here, it's like acupuncture, right? If you poke in the foot, your head falls off, right? Poke here, see what happens there. Poke here, see what happens there. You get it. But you do it on tiny databases. Therefore, again, I hope this is not taken literally here. Okay, that's just somebody is worried about medical things. Yeah? So let's do it on very small databases. You can run it thousands of times without having appreciable time overheads. Okay? Yeah. Okay. So here's the takeaway. So this is a new problem that was introduced here by us. Okay? Because one of the reasons we also want to highlight this is traditionally we have been taking Western problems, as they say, and then coming and doing a plus on it. Okay, so somebody does sorting there, so I'll do sorting plus and so on. Okay? It's very, it's been comparatively uncommon, although it's much improving in recent years, is for us to design the problems itself. We are very good at analysis in India. We're terrible at design. Okay? Given a circuit, all voltages, currents, tuck, I'll give. But if I say, can you give me a phase lock loop? What's that? Okay, how to do it. So design part is weak, analysis is very strong. So ideally, if we can design our own problems, then in a sense we are leading the world. Okay, otherwise we're just playing catch up with others. So this was a new problem that we introduced, and it has. I didn't go through all the other aspects. There are several use cases from a performance perspective or from a database migration perspective and so on. And we have a tool which can actually extract a non-trivial set of queries and fairly complex industrial strength benchmark queries, and can do this automatically without any human involvement. There's of course several challenging open problems to be solved, and if there are undergraduates here who have been enticed thanks to this symposium to come and join us in doing this, we have enough problems to keep you busy for a while. If you want to bring your friends along with you from you, please do that, okay? We can get it done. So there's a lot more details on our website, which is given here, which is the Database Systems Lab, Computational Data Sciences, Indian Institute of Science, then the ac.in network, and then this project is called as Hidden, but the link is visible, so you can get this. Right? So this is where you can go and see many of the technical details, but hopefully I just kind of illustrated to you why there are certain exciting problems that look easy to state, but are fairly hard to achieve. Okay? Yeah, so again, sometimes people say, okay, but you haven't done that query, which is very complex, which is my query. Okay? What I would say is that what is surprising is not how far we have to go. There's still quite a distance, but how far we have been able to come. Okay? And this relates also to the previous time attacks and so on. People will say, what about this attack? What is impressive is that how far we have come in terms of handling many of the more commonplace attacks. Okay? There will always be a fringe which you cannot handle so easily, but the number of things that you have actually handled is very important. Okay? So this is the surprise, is that we have been able to even reach this far. And of course, there is a long ways to go, but initially it was expected that we would just basically fall at the first hurdle and just give up on the problem there. But interesting enough, you can do lots of cute things by just looking at the problem in somewhat perverse ways and doing fancy tricks on it. You can figure out things. And if you are looking for an interesting problem, just think about this problem and see that everything that we looked at in the predicates there was like saying that age greater than 10 or age less than 20 or essentially positive constants. Suppose I said age not equal to 10, which is a negation operator. Can you go and extract it or from an opaque executable? Just think about this problem, okay? Okay. Yeah, so with that, happy to host any questions you might have. Yes, sir.
I just remember an interesting thing we tried when I was an undergrad. So I hope my undergrad institute has improved the security. So usually we get the grades, they announce the deadline and we get the grades.
Yeah.
But then you always want to see if you can get your grades before. We didn't want to modify.
Yeah.
Before.
Okay. So it's a read only thing.
They're scared, right? What if you're debarred? The government colleges again.
Correct.
So what happened was we realized that you need an admin level privilege to look at what faculty has uploaded.
Yes.
So we went to Wikipedia and then found a password expression that will Boolean by logically evaluate it to 1. Just copy from Wikipedia and put it.
Right.
We got admin level.
Correct.
No, we could potentially have modified.
Right.
But
No, absolutely.
the unfortunate part is sometimes I knew people who had gotten F grades.
Exactly.
Who said you're going to graduate in, let's say, a week's time or something. But anyway, yeah, I think hopefully they have improved. The security.
Actually, we're surprised. I don't think it has really have improved. Because this is what I was saying. This is much easier to do SQL injection attacks, exactly like what you said, where you put the value 1 and you make it true to true. So you don't require any of this hyphen covert channels and side channel attacks. So you just attack in the front door itself. Just break it down and go through, and you can do this. But many things are vulnerable, which is
Thank you for the interesting talk.
yeah, sure. Just promote the.
Like my question is, like you said about the SQL relation database.
Yeah.
There are some database like NoSQL like MongoDB also.
Okay.
Like how the attacks will be gone for that like databases.
Yeah. Okay. So what he's talking about is what's usually called as NoSQL databases, because basically people felt that the relational model with SQL was too restrictive, and we said we want to be like Salman Khan, we want to be bindas, we don't want to be restricted like this. Let's do arbitrary things. What you will find there is that there is no specific query language as such, but if you can take their application code and convert that into an equal SQL query. Then we can extract it here, because notice we are not looking at how you wrote the query, whether it was in Python, whether it was Java, whether C++, or native SQL itself, or even some other language. There's other languages like Quell and QB and stuff like this. As long as it's expressible in first and second order logic, that's another way of looking at it. If you can express whatever you are doing within this logical framework, then we can be extracted. It's not a problem to do that. But nobody stores useful information in NoSQL databases. All the corporate stuff is in relational systems. Okay. That's where the money is. Yeah, banking industry. That's where the money is. Okay. NoSQL is for all your Facebook networks. Who cares? Okay. Here the grades are there, as I said, right? Which is the most important thing. Grades and salaries are there. See, you could also do it for salaries. Right? Small zero added, nobody will notice, right? Small mutation. Say, oops, I put in a zero.
My question is regarding SQL Shield.
Yes, okay, yeah.
My question is regarding SQL Shield. So you said it takes all the structures and we cannot get access. Are there any decryptors so that we can get access?
Yes, the decryptor is at the very deep inside the database engine. So even the things that you would normally have been able to see on the surface itself are all encrypted, including the query execution plan, the logs, and all the supporting scalar functions. Everything is encrypted. Of course, it has to be decrypted finally because somebody has to execute the query and say what the answer is. But that's happening, as I said, inside your kitchen. So the danger has reached there. You would want to stop it at the front gate. So that's the difference. Ultimately, it would be known, but if you are going to wait till there are two problems. One is that there may be side effects where they, for example, go and modify some set of permissions and still look like an innocuous query. The second is that your database engine now has to check every query saying is it dangerous or not. And as was mentioned previously by Professor Chatterjee, the difficulty is that if you are going to do the checking there, your performance is going to suck. So you are doing your net banking. You will say, wait, I'm checking the query. Okay? The money is not being transferred yet. So you would not be able to support real-time applications with that kind of checking. So you want to do the checking offline and then say that the engine doesn't have to worry about this. So that the security part and the performance part are to some extent delinked from each other. Somebody does the checking and then lets you in. Okay? Then you do whatever you want.
So your input is the database and the encrypted query.
It's in principle it's only the encrypted application. The only reason we insist on a database is that otherwise I would have to create something which by trial and error would produce a non-zero result. But if you know that this original query that was given does produce a non-zero result on the original database that you had, then you can just use it from there itself. You can use your own original database as being the sample database. But otherwise, if there, because otherwise I may create synthetic databases on which the query gives no answer. It gives empty answer always. Then I cannot figure out anything because I need to keep looking at the output, how it changes in response to input changes. So that's the only requirement.
So how do you reduce the size of the database? You said you can eliminate half of it.
Yeah, so I cut it in half and then I run the application and see whether the output is khali or not. If the output is not khali, it means that even this half is good enough. If it became empty, it means the other half was good enough. So I do a recursive logarithmic.
How do you cut the
Okay. So now you're again getting to the medical thing. He wants to do surgery on the tables here. How do you cut it in half? There is two ways to do it. One is to make physical copies of the database, saying that there are n rows, n by 2 go here and n by 2 go here. But that's the ugly way because that's very slow. You can do what's called as virtual views on the table, where logically you cut it in half. And you said this is one part of the table and this is the other part, which can be done without explicitly, physically cutting it into two pieces. Okay? You put a mask on it, and then you can run it through that.
So you use some kind of marks to
Exactly. Right.
But your efficiency improves with masking. Right?
Yeah, exactly. Yeah, it's much faster. Yes, absolutely. By an order of magnitude. Yeah.
The lemma which you used in the database migration, so we will miss the OR part in the
Okay, so here we had assumed that these were all conjunctive predicates. What you pointed was very good. I think you can join our lab. Yes, so you are talking about disjunctions, which I had not covered here. And disjunctions are hard to extract, especially if there are multiple disjunctions which are connected by conjunctive predicates. So you could say age is equal to 10 or 20 and name is equal to Jayant or Sumit. If you have multiple, how do you figure out that these two are separated pieces and they have an intermediate and correct connector? But we have done some work on it. We can talk about this offline if you like. But disjunction is much harder than AND to do. You're right.
Not then, let's thank Professor
Thanks very much.
for nice
Thank you.